So I'm Janek van Oirschot. I will be talking about hardware loops in the IPU backend. So first, some context. IPU stands for Intelligent Processing Unit. It's the chip that we at Graphcore develop. It's a chip with many cores, or as we would call them, tiles, with inter-core communication. Each tile has its own memory as opposed to having a shared memory pool for all tiles. Each tile has multiple threads, and each thread can have two execution or pipelines, which can be run in parallel when bundled. One main for integer instructions and registers, and one auxiliary for float instructions and registers. So the granularity of this talk is really limited to a single tile, and even a single thread, really. So this talk uses the plural hardware loops, and that's because we are targeting two instructions as part of our hardware loops in the IPU backend. One is the RPT, or repeat instruction. The other is the BRNZ-DEC, or branch if non-zero decrement instruction. So first, the repeat instruction. It precedes the loop body that it tries to loop. It takes in a trip count and the number of bundles within the loop body. A quick example here where we see 3 bundles. I should add that the number of loop bundles in the operand is offset by 1, hence why we see 2 of them. Then we have the branch non-zero decrement, which is a bit more traditional of a branch instruction. It takes in a value to be tested and decremented, and a target address to branch towards. So some of the characteristics and constraints of either is that the repeat, the trip count that it takes, depends on architecture. So we have different sizes for different architectures. It requires the instructions within the loop body to be bundled. The maximum number of bundles within the loop is limited by the encoding size that we have, which is 8 bits with an offset that's 256 bundles. Implicitly, it skips over loop bodies in case the trip count is 0. And on top of that, there's a constraint on the type of instructions that can occur within the loop body. So we don't allow control like branch or system like trap instructions. As a result, we don't allow any nested loops within a repeat loop. The branch non-zero decrement has a trip count limit to 32 bits, which is the bits available for the registers. Its range has 19 bits available for it, but since we access word sizes, we can offset that by 2, so we have basically 21 bits of range for that. So to kind of compare back to the example that I showed, we see some of the constraints here where the loop body that I've encircled in the yellow kind of circle are all bundled. It implicitly skips over the loop in case the trip count is 0, so we don't need to precede the repeat itself with a branch that goes over the loop. The branch non-zero decrement does need the branch over the loop, and also needs to have an adjustment of the trip count. And of course, we have the branch instruction in the loop body itself, adding a single cycle to each iteration. So now we are all experts on the IPU hardware loops, but how does that affect our the IPU backend? So here we have kind of the high-level overview of all the related passes and stages for our hardware loop. So we have the hardware loop IR pass, we have the Colossus loop conversion IR pass, where Colossus is kind of the architecture family name. You'll see it pop up more often. We have ISTIL lowering, the software pipeline. I kind of left that out of scope for this talk. And finally, we have the Colossus hardware loop MYR pass that will emit the MYR instruction for these hardware loops. So the first pass, the hardware loop IR pass, in our case, this used to be a custom pass, but we've since moved towards the target-independent hardware loops pass. It is run as part of the code-gen prepare passes as opposed to the add pre-ISL passes that a lot of other targets put it in. Reason being is if we place it any later than the codegen prepare passes, it will have removed the assumptions, and we make use of the assumptions actually. So if anyone has worked on hardware loops, they will be familiar with the is hardware loop profitable target transform hook. As a developer, the goal of this is to return true or false, depending on whether the hardware loop is actually profitable, but also to populate the hardware loop info struct as required for your hardware loop. In IPU's case, we do some processing of assumptions within this hook, and we emit or we kind of populate the struct different depending on whether we wanted to repeat or a branch on zero decrement instruction. So here we have the actual code that populates this struct. So first off, we have the is nested legal. That one is technically true for both. We just have to make sure that in the repeat case, it is the innermost loop. Counter register to kind of denote whether the induction variable is hidden within a register within or a user accessible register. Then the count type, which is really I64 or I32, depending on the bit width. Then the loop decrement, which just tells with how much we decrement at each iteration. And for repeat case, we also have the perform entry tests to kind of model the semantics of being able to elate the loop body. So with that, we emit the following 4, or basically 8, but 4 intrinsics. We have the LLVM test set loop iterations intrinsic, which is in case we want to repeat, and it's put right outside of the loop preheader. Then we have the LLVM start loop iterations, which is put in the preheader itself, which the preheader is the basic block that dominates the loop body, and it's always run before we run the loop. That one is emitted for the branch on zero decrement. Then we have the loop decrement register, which gets passed this induction variable of the previous intrinsic emitted as part of the loop itself. And then we have the loop decrement without the explicit register, which is emitted as part of the repeat. So to finalize our implementation of this hook, the repeat is prioritized over the branch on zero decrement, and the constraints that we kind of check are so whether the repeat is the innermost loop, so whether it has a subloop or not, and also whether the range is fit for these instructions. So in repeat's case, we have the is within repeat range, which uses scalar evolution to deduce the trip count and see whether that fits within repeat. But we also have the is KB valid for known bits, where we use compute known bits and the assumes to see if the user has given us any hints on whether we can actually emit a repeat. In addition, with some trivial architectural constraints. With branch on zero decrement, we kind of do the same, but only for the range check, where we have the scalar evolution version and the kind of compute known bits version. So in kind of conclusion of this pass, it takes an LLVM and emits LLVM with hardware loop intrinsics. Then the next pass is the loop conversion IR pass. It is run as part of the add pre-ICEL passes. It's a very mechanical pass, so it takes in the previously defined intrinsics and emits the IPU alternatives, basically. The reason we have these is it kind of stems from the time where we still had a custom pass for this. So these are basically the intrinsic that we used to emit directly. Now we have a pass that kind of converts between the two. So here's an example of the case with a repeat where we see the test set loop iterations, hardware or target independent hardware loop intrinsic, which gets expanded into 2 different intrinsics, which is the Colossus C loop guard. C loops stands for counter loops and kind of our name for hardware loops. That one has kind of the same semantics as the test set loop iterations, but in addition to that, it also has the Colossus loop begin, which basically takes in the trip count and makes a induction variable, which puts it put that in the pre-header. Then we have the loop decrement intrinsic, which gets expanded into a Colossus C loop end intrinsic, which returns a pair, one being the updated induction variable, so the induction variable gets decremented, and the other being the Boolean value on whether we should branch back to the body or exit out. In addition to that, we have an argument to denote whether we are targeting a repeat or a branchless error decrement. This one gets propagated all the way to the end, basically. In our case, it's 0 is a branchless error decrement and a 1 is a repeat. In conclusion of this pass, takes in LLVM IR with the target-independent hardware loop intrinsics and emits the LLVM IR with the IPU hardware loop intrinsics. Then comes ISL lowering, where we take in these intrinsics and emit ISD nodes. So the Colossus C loop guard intrinsic gets lowered basically one-to-one with the C loop guard branch ISD node. It does subsume some extra instructions that also do the branching and becomes its own branch instruction or branch ISD node. And then we have the Colossus C loop begin, which gets expanded into two ISD nodes, one being a C loop begin value, which is basically one-to-one in terms of semantics. But in addition to that, we have the C loop begin terminator, which becomes the terminator of that basic block. So it's at the end. Then we have the Colossus C loop end intrinsic, and each of the values in the pair becomes its own ISD node. So we have the C loop end value, which does the decrement and updates the induction variable. And then we have the C loop end branch, which does the branching similar to what we've seen with the guard, the intrinsic and ISD node. Then afterwards comes instruction selection. So we take the ISD nodes and kind of lower them in pseudo instructions of the same name. The mapping is almost one-to-one. We just switch around some operands occasionally, but we don't add or remove any information at this stage. So it's a one-to-one conversion. So in conclusion, ISL lowering takes an LLVM IR with IPU hardware intrinsics and emits the LLVM MIR with the IPU hardware loop pseudo instructions. Then comes the hardware loop MIR pass, which is run as part of the add pre-emit pass, which is after register allocation, but a couple stages before emitting assembly. Goal being remove all the pseudo instructions and emit the MIR of the hardware loops. The reason it is so late within the pipeline is because at this stage we can actually count the bundles required for the repeat without having to be concerned with more code transformations afterwards. So here is an example, kind of the same example I showed before, just at another stage, where we have the MIR with the pseudo instructions, all 5 of them. We have the guard branch, we have the begin value, the begin terminator, we have the end value and end branch, and that gets transformed into the repeat equivalent. And how it does that is by, we remove the C loop guard branch because we get that one semantically for free with the repeat. The C loop begin value just takes the M2 register and puts it in the M2 register, can be removed. The C loop begin terminator, and here we kind of see why it was necessary, is that pseudo instruction gets pushed into the loop body as the first instruction of the loop body, and to make sure that the M2 register doesn't get clobbered in the meanwhile, and that one gets converted into the actual repeat instruction. The C loop end value, we get that for free repeat, similar with the actual branch, we get that with the repeat instruction itself. I should also add that if any of the constraints of the repeat are not met within this pass, we can always fall back to trying the branchless zero decrement equivalent. So a quick note on our users. Most of our users are internal, and they're working on the poplifts libraries as part of our popular software stack. They are what I would consider power users because they are very comfortable and aware of the IPU architecture and know how to really squeeze performance. So what we often see is that they would use C++ in conjunction with some assembly calls or calls to assembly that they've written. And we try to convince them to, instead of writing assembly, to use C++. So we kind of provide some options for them to still get these hardware loops in case they use C++. So one of the options is the assume. And this is where I tell you that I have been lying to you all, that I've been showing the topmost code, which I showed emitting a repeat, but actually it doesn't, because the size is the trip count, and we cannot really infer whether the size is within the repeat trip count range. So it will always be conservative and emit a resonant zero decrement. But if we add the assume and just make sure that it's within this repeat trip count range, it will emit a repeat, actually. Another option is that we have the repeat size t, which is a unsigned int type, which can be used as the trip count to target repeat instructions, or if you use it within as a trip count of a loop, it will make sure that the repeat size t is within the range of a repeat instruction trip count. It will also change depending on what architecture you're compiling for. One thing is it is C++ only. It uses bit int n, which is I believe a C23 proposal. We just wrap it with a lot of templating to make sure that it works well with other types and other sizes. Where we see here the example on the right with the uppermost function bar, where it cannot decipher whether it is a repeat. We can fit within a repeat, so it will emit a resonant zero decrement. And the other two will use the repeat size t as a trip count and induction variable, and will in fact emit a repeat loop. I did omit one of them, but it emits a repeat loop. Finally, something that's more of a work in progress is using pragmas, because not all loops can be defined within as a trip count or as an induction variable. Like if you have a container, if you have a check on container where the container is empty and kind of loop on that, we still want to give users the ability in those cases to emit or to emit a hardware loop. So we're thinking about adding these pragmas for them to use on a loop level basis or loop level. So we have the force any, force repeat, force resonant decrement, and none. There's a proof of concept out there that we made, but it's not set in stone yet. So yeah, I hope I've explained a bit of a history, the present, and a sneak peek of the future of hardware loops in the IPU backend. Thank you for your time.
Any questions?
Hello, very nice talk. I have a question about performance. So you mentioned that the power user, you're trying to convince those power users that write directly assembly to switch to C++. And I was wondering, do you have any sort of figures of how performance comparable, like comparing something like I would imagine like a matrix multiplication, something written in assembly and written in C++ through your backend would compare? Is that completely different, or they are comparable right now?
Yeah, good question. We kind of have a lot of granularities within our software stack, and our users are on a bit of a higher level. And our granularity, we don't really have good benchmarks, at least not yet. And they're kind of, they also have a lot of code that do the communication between the tiles, and it kind of becomes hard to really decipher which cycles are actually compute and which ones are the communication between them. So it's hard for us to really use those numbers. So we kind of have to come up with our own benchmarks, and we are working on that right now. Yeah.
Okay, thanks.
More questions? Yep.
Hi, thank you for the talk. It's more of a hardware question, but do you have a loop initialization cost? Hardware loop or I can say it. A hardware loop initialization cost in your hardware loop instruction or not? Like, because at Canary, we have to wait a certain number of cycles after the hardware loop instruction in order to initialize it. I don't know if you've got the same in Graphcore or not.
It's a bit hard hearing you. I think that the speakers are towards you guys, so it's kind of hard.
Okay, I can maybe talk like that. Is there an initialization cost in your hardware loop instructions or not? In
you mean in terms of cycles? Like?
Yeah, in terms of cycles.
No, all our instructions are single cycle basically. So it's
okay.
Yeah.
Okay, nice.
Other questions? Right, if not, let's thank our speaker again.